Hi everyone, welcome to our second SNAPP seminar of the spring semester. So today we're very happy to have Pengyu here presenting to us on his recent work on optimal incentive design in decentralized dynamic matching. So Pengyu is an assistant professor in the Operations and Technology Management Department at the Questrom School of Business, Boston University. Research studies the design and analysis of marketplaces in dynamic settings using tools from probability, optimization, and game theory. He is interested in foundational models driven by challenges in sharing economy and the allocation of public resources. His research emphasizes algorithms or mechanisms that not only have good theoretical guarantees, but also are simple, robust, and hence practical for real-world systems. Pengyu is the recipient of many awards, including the Inform's JFIC Best Paper Prize. He earned his PhD from Columbia Business School and his bachelor's degree from Peking University. Okay, so Pengyu, the floor is yours. You have until 12:30 p.m.
Sounds good. Thank you so much, Yue. So I'm so happy to be here. My name is Pengyu Qian. I'm from Boston University. So I remember 5 years ago when I was still doing my PhD, it was in the depths of COVID. We had this pilot season of SNAPP seminar, and I attended all the earlier ones in that and learned a lot. So now it's already in season 5. I'm happy to have this chance to contribute, to share something I'm recently very interested in about, and I look forward to the discussions ahead. Okay, so this is a joint work with two of my wonderful collaborators, Chen and Jingwei. So in this work, we study dynamic matching, but in a decentralized setting, where you actually need to design incentives to motivate the agents to participate in the matching. As you soon see in a few slides, so it's motivated by very important real-world applications. Okay, so I know many of you in the audience are experts on dynamic matching, but just to make sure everyone is on the same page, let me give you a 4-minute crash course on dynamic matching, right? So what they're considering, what's the state of the art. The example I want you to have in mind throughout the talk when I talk about dynamic matching is kidney exchange. Because for one, it's useful to have a concrete example in mind. Secondly, kidney exchange is one of the key motivations of the settings of our work. So here's how kidney exchange works. Let's say I'm in need of a kidney transplant and my wife is willing to donate to me. But unfortunately, we are incompatible with each other because of blood type or tissue type incompatibility. So what we are going to do, we're going to go to a large hospital which has an exchange pool, and we enlist our donor patient pair information. In their exchange pool, they have hundreds of such donor patient pairs, and it's possible we find another pair which is also internally incompatible, but we are cross-compatible, meaning the donor there can donate to me and my wife can donate to the patient there. Right, so on the right-hand side, I'm writing this in the language of dynamic matching, right? So you have multiple types of items. By item types, you can think of them as the blood type combinations, right? And by items, you think of them as the donor-patient pairs. There's a compatibility graph, meaning some types can be matched, some types cannot. The items, they dynamically arrive and depart. And different matches, they generate heterogeneous match values. And I want to point out matching doesn't necessarily have to be bipartite. It could be multi-way matching. So for example, in kidney exchange, there are these 3 chains or longer chains. Imagine finding 3 donor-patient pairs. Donor 1 can donate to patient 2, donor 2 donate to patient 3, donor 3 donate to patient 1. Right? So in the language of dynamic matching, we have a 3-way match. Right? So this match consumes 1 item 1, 1 item 2, and 1 item 3. Right? So that's the setting of dynamic multi-way matching. Many types of items, many types of matches, arrival, departure, and heterogeneous match values. And the decision here is to decide who to match and when to match. So for example, you have multiple potential matches that can be made, which one to perform. And also, do you do the matching greedily or do you wait to thicken the pool? Right, so there are many amazing recent works on dynamic matching. And by no means the list here is exhaustive, right? So there are works that study bipartite matching, right? So how to design the algorithm that maximize revenue and how to analyze the steady state of a system given certain policy. There are also works that study so-called low regret algorithms who benchmark their performance against the hindsight optimal performance. And they get this constant regret type results. And many of these work, they consider a setting where items don't depart. There are also works that consider the setting where items do depart, right? So in that case, it becomes more challenging because each item only has a window where it's available for match. So this dynamic matching. And today's talk is not about a new algorithm for dynamic matching, right? Instead, we ask a different question. And that brings us back to the word decentralized in our title. So what do I mean by decentralized and what motivates this decentralized setting? The motivation is coming from multi-hospital key exchange, right? As I mentioned earlier, okay, so we as a donor patient pair, I can go to a hospital, enlist in their exchange pool, but there are more than 100 such big hospitals in the US. And about 2 decades ago, there was this proposal to form a national platform, right? So what about all the hospitals? Everyone submit all the donor patient pair to the national platform to form a much thicker pool, which in this case means better matches, more efficient matches. Why is that? Because if you have thicker pool, it's more likely you'll find a match quickly. So it's more likely you'll find a match before you depart from the system. All right. So that's the benefit of resource pooling. What's the challenge? As you can imagine, right, the challenge is hospitals that are self-interested. They will not just willingly submit all the donor patient pairs. And this phenomenon observed empirically is called free riding. So just think about the problem in this way. So not all the pairs, not all the items are created equal. Some are more valuable because they are easier to find matches. So they are highly sought after. There are also items that are hard to find matches. They are hard to match. So there's an oversupply of them in the system. So what was observed is if you just have this vanilla national platform, hospitals, they will just withhold easy to match pairs for their internal matching. And they only submit the hard to match pairs to the national platform. As a result, the national platform is full of hard to match pairs, which is not efficient and kind of beats the purpose of having a multi-hospital kidney exchange. Right? So this actually is a form of negative externality, right? So what's bad for individuals is not bad for global optimality, right? And this was mentioned in the earlier paper by Ashlagi and Ross. This is a big issue in practice, right? It's mentioned as one of the key obstacles by the CEO of a national kidney platform. Right, just to understand it mathematically. So here's an example from the earlier paper. So even though we consider dynamic setting, and this example is the static setting, still the idea is the same, right? So the conflict of interest is the same. So here in this kidney exchange, there are 4 items, right? 2 belong to hospital A, 2 belong to hospital B. And there are 2 possible matches. One is a 2-way match between A1 and A2. One is a 3-way match among A2, B1, and B2. Right? So, and let's assume the hospital's objective is to maximize the number of items matched. So what's best for hospital A is the internal match, right? They get a utility of 2. They have 2 items matched, but that's not optimal for the system. What's optimal for the system is to do this 3-way match. A2, B1, and B2 has a utility of 3, but that will make the system better, but hospital A worse off. So you see what's best for hospital A is not best for the whole system. Right, so this leads to the research question. Right, so it's a design problem. Think about how to design a decentralized dynamic matching market. And the challenges in this problem are nicely summarized in a very comprehensive survey paper by Itala Ashlagi and Alvin Roth in Management Science. It's called Kidney Exchange and Operations Perspective. Right? It mentions that in multi-hospital kidney exchange, the key operation components involve both submissions and matchings. Okay, so not just matchings. Incentivizing submission is also very important. And although after all these years of work, we still need further study of dynamic mechanisms to control the incentives for hospitals to participate fully in the multi-hospital kidney exchange programs. Okay, so what's the state of the art, right? So we'll have people down in the literature on this front. There are two very related streams of work. One is the one I listed a couple of slides back. It's dynamic matching, but in a centralized setting. There's no incentive, there's no submission. The controller has full control over all the items. They decide who to match and when to match. And there are works that study how to design a multi-hospital kidney exchange, considering both matching and submission, but the model used there are overwhelmingly static, right? So earlier works consider a random graph model, a bunch of vertices, each represent an item. A hospital owns a subset of the vertices. Right? There are also works that use a static optimization problem, which can be thought of as the fluid approximation of the matching problem, considering the primal and dual and derive some insights from it. There are also other works based on static graph and study the Shapley value. So to the best of our knowledge, our work that I'm going to cover today is the first one to consider a decentralized dynamic matching market. Its dynamic model also considers the incentive issues. So why do we need to consider dynamic setting, dynamic model? Because many of the negative externalities, many phenomenon cannot be captured in a static model. For example, items, they come and go, right? So they depart, that creates a friction in the matching. And this cannot be characterized in a static model. Okay, and many behavior in dynamic models cannot be characterized in a static model. And also studying this dynamic setting, actually, it brings a lot of challenges. Right, just think about it. It's a large dynamic stochastic game. Many players, each player has a large decision space and state space, the matching decision, submission decision, and we also have a large design space, right? How to incentivize agents to participate. And in this work, we're trying to overcome all these issues and design some interesting dynamic mechanisms. Another interesting application of the decentralized dynamic matching setting is actually ride sharing. Right? Just think about the works on ride sharing. If you're operating one ride sharing platform, you need to solve a dynamic matching problem. Right? Items are drivers and riders from different locations. But recently, we are seeing this platform integration, meaning there are multiple platforms that collaborate. Right? Those supposed to be competitors, they collaborate. For example, the Curb and Via, they're two ride-sharing companies in New York. Since 2017, you can book both services from either platform. That means they are pulling their riders and pulling their drivers. And this map app in China, so it's called AMAP, Gaode map. So actually, it integrates dozens of ride-sharing platforms. You can order ride from any of these platforms. But just think about the incentive issue here. Right? So how do we incentivize those cooperating platforms to fully submit all drivers and riders? Right? Will they withhold some and will they submit everything? How to split the commission? How to design the incentives? So this work is part of our ongoing research program, which is to think about a marketplace design problem, which is how to incentivize resource pooling in the private information setting. By that, I mean, as an agent, I only know what I'm doing. I don't know what other people's states are, what their arrival processes are, right? So because this will make the prescribed mechanism more useful in practice. And we want to incentivize resource pooling for queuing setting, matching setting, and general stochastic systems. And we try to develop a technical framework to do that. Speaking of which, we have an earlier work together with Chen and Yilun, studying incentivizing resource pooling for the queuing setting, how to motivate queues to collaborate. And this work is about the matching setting. Great, so here's an overview of what I'm gonna do next. Right, so I'm first gonna introduce the model. We study a general setting. There are many agents, each will be performing a dynamic multi-way matching problem with private information. And we're gonna propose solutions. We're gonna propose two mechanisms. One is called marginal value mechanism. One is slightly more elaborate. It's called marginal value plus credit mechanism. And we're gonna provide theoretical guarantees, right? We will show that they do motivate full submission. For marginal value is in the sense of approximate Nash equilibrium. For marginal value plus credit is in the sense of mean field, AKA oblivious equilibrium. Great. Any questions so far? If not, I'll just jump right into the model part.
Pengyu, can you hear me?
Yeah.
Okay, I have a question about the kidney allocation example.
Yes.
So I want to understand a bit better of what type of strategic behavior hospitals can assume. So for example, so right now, isn't it the practice that so the kidneys donated would be first allocated to a smaller geographical area around the hospital, and then if there is no match, and then will sequentially be offered more broadly to farther to the national waiting list. So here, so when I think about the strategic behavior of hospitals in terms of submitting to the national list, so what behavior or actions am I thinking about?
That's a great question. So first of all, there are two major ways to allocate kidneys, right? One is through kidney exchange, one is through waiting list. Right, so kidney exchange deal with this live donor kidneys, and for deceased donor kidneys is through waiting list. I think that the one you mentioned, this area, like a radius 250 miles, that's for the waiting list mechanism, right? And the hospital will have different set of strategies in that setting.
Right.
Right. In here in kidney exchange, it's mainly withholding this pair or submitting them to the platform. That's the decision they make.
Yeah. Okay. Got it.
Great. Thank you for the great question. Yep. Great. So in the next few slides, I'm going to talk about a model. First, what does a network look like? Okay, so different agents in our model, they might have different dynamics for their items, but they do share the same network topology. So we start right here. We have many types of items. Here I'm using different shapes, like 1, 2, 3, 4. And there are different matches that can be made. Right, the number 1, 2, 3 here. And each match has its own constituents, right? So we use the matching matrix to represent that. For example, a type 1 match requires one item 1 and one item 2, right? So we can use the matching matrix to denote that. M11 equals to 1, M21 equals to 1. That's the constituency matrix. One match 2 consumes one item 1, one item 2, and one item 3. Right, we record that in the matching matrix. One type 3 match uses one type 3 item and one type 4 item, and so on. Okay, so that's the network of the match. And we have, now let's define the agents and dynamics. We consider a continuous time setting, infinite horizon. So there are many agents, each managing its own local dynamic multi-way matching problem. Okay, so the agents problem, they differ in the arrival rate. So for, let's say for agent I, the arrival rate of type J items is lambda ij, right? That depends on both the agent and the item type. But the departure rate is only item type dependent. Okay, it doesn't depend on the agent. Right, think about the example of kidney exchange. Again, like how fast people's situation deteriorates, how fast they depart, it doesn't depend on the hospital they register at. And performing a type N match generates a reward of RM. Agent's objective is to maximize infinite horizon average reward. So any questions so far about network, agents, and dynamics? Great.
Yeah, so I just typed my question. Yeah. So is the matching matrix a symmetric matrix?
Not necessarily. Right.
So I'm not
You
sure
think,
about like the exact meaning of the MIJ. Yeah. So oh yeah,
I think
MJ.
the matching matrix is not even a square matrix, right? So you
Oh,
just records for each match how many of each item does it need, right? Just a constituency.
so like the J is the donor and M is the receiver, or
Right. So thanks for the clarifying question. J is a type of item. M is a type of match.
oh,
Right. So MJM means I'm conducting a match M. How many type J items do I need?
okay.
Yeah.
Okay, thanks. Yeah.
Thank you. Great. So now let's go to the market design part. Right. I just described many agents, each solving a dynamic matching problem. What about submission? Now let's give each agent another action to take, which is submission. At any time, they can submit any one or any subset of their currently owned items. Okay, so when they submit, they'll submit to this thing, the construct that we call a meta platform. So this meta platform, it will just keep doing centralized matching all the submitted items, right? You can see in the illustration here, I use different colors of different types of items. For example, this blue one, it indicates it comes from the blue agent, right? The orange one, it comes from the orange agent. So when you perform a match, maybe the constituents, they come from different submitters. Right? That's what's going on in the meta platform. And the design question, of course, is how to reward submission, how to incentivize them to submit. I'm intentionally refraining from defining the design space, because the design space is huge, right? The reward, it can depend on item type. It can depend on whether the submitted item ends up getting matched or not, right? And the reward can take many forms. It could be awarding priority for future matches. It could be awarding credits that are useful in the future. It could be a more favorable splitting of the reward, right? All kinds of things. So I'm not defining the whole design space. I'm just going to define two specific designs, right? Two specific mechanisms and analyze their performance. Great. Right, so let's take a closer look at this meta platform. So what's going on in this meta platform and how it centrally matches the submitted items. So we want our result to be as agnostic to the algorithm used here as possible. So here's the only thing we require of the meta platform. We assume it performs a periodic centralized matching. And the distance between two matching epochs is delta. And the only way our mechanism's performance depend on the algorithm used here in the meta platform is through the regret of the centralized matching. So basically, if you use a better centralized matching algorithm here, we'll get a stronger result for our mechanism's performance. But it's the analysis is modular. You can use all kinds of algorithms in the meta platform. Great, so any questions about the model? Wonderful. So now let me introduce our first mechanism. So it's called the marginal value mechanism. Right. So before proposing this mechanism, let's first take a look at the fluid or first order approximation of the underlying matching problem. Right. And this fluid problem is called the static planning problem. Right. It's a linear program, tells you what's the upper bound of the performance of the system. Right. On the right-hand side, I'm just reminding you of the definitions I introduced earlier. Left-hand side is the SPP, the static planning problem. The decision variable here in the LP is the average rate of conducting match M. Right. So the objective is maximizing the rate of generating reward and summing over all types of matches. Type M match has a reward of RM and conducting it at rate XM. right? That's just reward. And the constraints are resource constraints, right? Because the arrival rate of type J item is lambda J, right? So lambda J here is the total arrival rate of item J among all agents. Okay, so the rate I match cannot exceed the rate the item arrives. Left-hand side is summing over all matches, how many type J item it consumes, and what's the rate I'm conducting those matches. In total, that's the rate I'm consuming type J items. It cannot exceed the arrival rate of type J items.
Pengyu,
Yeah.
I have
Yes.
another question about the model.
Mhm.
So I understand the arrival rate of the items, and then so and then they are also characterizing different types of matches. So what is the implicit assumption on the demand itself? So I'm just thinking that so for each individual agent, so they submit their available resources to the Meta platform, but you need to match. So the matching should be done between a resource and a demand, right? So am I missing something about? But I haven't heard you talk about demand at all.
Thank you for the clarifying question. So here, yeah, it's actually matching among the resources, right? So it's matching among different types of items. If you think about a bipartite match, right, you can define half of the item types as supply, the other half as demand. But if it's multi-way, like this, you can think of it as all resources. You can do any match. Yeah.
I see. So so by submitting resources, so is it essentially equivalent to so the agent can submit either a resource or a demand or a request for a resource?
Let's see. I think there's only resource. Right. So I'm calling a resource, but actually it's an item. Think of it again as a donor-patient pair. Right? A donor-patient pair only needs to be matched with another donor-patient pair.
Okay, got
Right.
it.
Yeah.
What about sharing platforms?
Right, that's a good question. So sharing platforms, yeah. So then in that case, items, they are categorized into riders and drivers, right? And in the centralized matching problem, in the Meta platform, you can only match riders with drivers, right? That's reflected in this compatibility graph, right? You cannot match riders with riders, but you can do these pooled rides, maybe multiple riders, one driver. It's possible.
Okay, thank you.
Great, thank you, Yue. Right, so that's the static planning problem. Okay, so now let's talk about the value of each item. So as I mentioned earlier, not all items are created equal. Some are more valuable, some are less valuable. Let's look at a simple example. Just one match and two types of items. They have the same departure rate. Item 1 arrives at a slower rate. Item 2 arrives at a faster rate. So if you think about it, the system will be full of item 2s. Item 2 is oversupplied, and we are in need of item 1. So we say item 1 is over demanded, item 2 is under demanded. And let's say you have one more item 1. How much marginal value it brings to the system is R, right? Because it facilitates one more match, because system is full of 2s. But you have one more item 2, the marginal value is 0. It doesn't facilitate new match because there is already too many of them, right? So for general matching setting, not a simple setting, how do we determine the value of each type of item? We solve the dual of the static planning problem, right? So we write down the dual. The decision variables here are P's. They are the shadow prices for each type of item. We solve for PJ star. PJ star, where J is the type of the item, is the marginal value or shadow price of item J. All right. And there are two cases. If the marginal value is strictly positive, then we say this item is over demanded. If the marginal value is 0, we say it's under demanded. Okay, and we look at the primal static planning problem. Let's solve the average matching rate. If a match is conducted at strictly positive rate, then we say the match is essential match. If it's conducted at 0 rate, we say it's a non-essential match. Right, so those are the definitions we are going to need for the following slides. Right, so some matches are essential, some matches are not. Some items are over-demanded, some items are not. Great, now let's introduce the marginal value mechanism. It's very simple to describe. So it's about how to reward the submissions, right? So let's look at the meta platform. Let's say in the meta platform, we are about to perform a match M. There are two ways to implement this mechanism. First is the monetary implementation, right? Let's say we conduct the match M in the meta platform, then we split the reward in the following way. So it has constituents. The submitter of J will receive a monetary reward of PJ star. Right? So we just split the reward RM in terms of the shadow prices of each participating items in that match. And why is it feasible? Why can we split the reward in that way? It's because of the complementary slackness, right? Because we have complementary slackness and because the M we conducted is essential. So by the way, we will only be conducting essential matches in the meta platform. And this implies exactly I can split RM in this way. Right? Submitter of J gets PJ star. Right, so that's the monetary implementation. We can also consider the non-monetary implementation. For example, in kidney exchange, you cannot pay the hospitals. But the hospital's revenue comes from conducting transplants, performing transplants. So what we're going to do is the following. Let's say we're about to perform match M. We do a randomized policy. So the submitter of item J, that hospital, gets to perform the match M with probability proportional to the shadow prices. Okay, so let's say I'm hospital A, I submitted an over-demanded type of item. Another hospital submitted under-demanded type of item, we match. Then I get to perform this transplant. I get all the revenue, right? Because my submission has a higher shadow price. If you submit an under-demanded item, your PJ star is 0, you don't get to perform the transplant, the operation. You can see in expectation, these two are equivalent, right? So basically, the reward you get is proportional to the shadow price of your submission. Okay, and you can think about in ride-sharing setting, what does this mean? Right, in ride-sharing setting, we can do the monetary implementation, right? We can pay. The question is how to split commission, right? Let's say platform A's rider matches with platform B's driver, right? A ride is done and we have commission. How to split this commission among the two platforms? Right? We can think of it in this way. In rush hour, for example, there's a shortage of drivers. Drivers are more valuable, have higher marginal value, right? So the submitter of driver, that platform, gets a higher split, or they get all the commission. In the non-rush hour, we don't have enough customers. In that case, the submission of the rider, that platform, gets all the commission, right? So this is what a marginal value mechanism would look like in that setting. Okay, so what's the performance guarantee of the marginal value mechanism? What can we say about the equilibrium? Let's make some mild regularity assumptions, right? So the first assumption is about system growth. Basically, when the number of agents increases, the total arrival rate also increases linearly. The second assumption is saying that we don't have one agent that possesses a large portion of all the items, right? So the size of each agent's problem are roughly proportional to each other. Okay, so under this assumption, we have the first theorem. It's saying, okay, if the meta platform doing anything asymptotically optimal, then under the marginal value mechanism, full submission is an approximate Nash equilibrium. All right, so moreover, the suboptimality in this approximate Nash equilibrium, meaning how much I can improve beyond full submission, the suboptimality is of the same order as the suboptimality of the centralized matching policy. which means in this meta platform, if you use a better policy, a smarter policy, then as agents, I have less incentive to deviate, right? Otherwise, I have more incentive to deviate. That's how our results depend on the algorithm we use in the meta platform. Any questions? Great. Right, so a corollary, so let's be more concrete. So let's say in the meta platform, we set the matching epochs to be n to the power minus 1/3 apart. And we use this periodic clearing policy in the paper by Karimov, Ashagi, and Gurvich. Then we can show that full submission is an n to the power minus 1/3 Nash equilibrium, right? So meaning that the best I can improve by deviating from full submission is diminishingly small, is n to the power minus 1/3. And if you have additional assumptions, such as non-degeneracy on the overall network structure, then you can get better performance guarantees. Okay? Great. So what's the intuition of the theorem? It can be, we can think about the intuition in terms of the following linear program. Right, so remember previously we derived the static planning problem for the whole system. Now let's try to derive the static planning problem for agent I with submission. Okay, so the decision variables here are, what's the average rate of matching, doing internal matching, that's X, and what's the rate of my submission of type J item, that's S. Right, so my reward will include both the matching rewards and the submission rewards. If I submit J, I get reward PJ star. And the constraint is that my arrival rate of type J item is only lambda ij. So the total of the items consumed by matching plus the item consumed by submission should not exceed my item arrival rate. Again, resource constraint. All right, and we can derive its dual. So what do we observe from this primal and dual? We do some eyeballing, and we find the optimal solution to the primal and dual problem. Right, so we find a feasible pair where x equals to 0, s equals to lambda, p equals to p star is feasible solution to primal and dual problems. Therefore, it must be optimal solution. So let's look at this solution. What does it mean? X equals to 0 means I do not do internal matching. Okay, my internal matching rate is 0. S equals to lambda I means I submit everything. I submit everything to the platform. P equals to P star means the marginal value of each item for my local problem is exactly the same as the marginal value in the global problem. Okay, so the performance upper bound of an agent is given by submitting everything. Take into account the stochasticities in the centralized matching problem, we get our desired result. So that's the intuition. Any questions? Great. Right, so now we are reasonably happy. So we have a reasonably good result, reasonably good mechanism. But still, if we want to dig deeper, a natural question to ask is, okay, so full submission is approximate Nash equilibrium. Do agents still have incentive to withhold? Do they have incentive to deviate? And is it easy to find a way to deviate that beats full submission? Then we come up with this following simple example, right? So there are just two types of items, same departure rate. Type 1 item is over-demanded because we have relatively few of it. Type 2 item is under-demanded because we have a lot of it. The arrival rate is 3. Let's say each agent is identical. They all look like this. They all solve this problem. All right, so now let's imagine yourself as an agent. We're trying to game the system. We're trying to do this joint submission matching problem. So when we submit a type 1 item has a marginal value of 1. When I submit it to Meta platform, with some probability it will be matched. I will get a reward 1, right? With some probability it will not be matched because it might depart before getting matched due to the suboptimality of the algorithm using a central platform, etc. So let's just assume the probability a submitted item gets matched in the central platform is some W, which is strictly below 1. Right, so you submit an item with 99% probability it gets matched, right, for example. Okay, so given that, your first policy is just submit everything upon its arrival. And compare that with another policy. Right? In policy 2, as an agent, we secretly maintain a safety stock for the under-demanded type 2 item. And the safety stock level is 1, meaning, okay, if I don't have any type 2 item, next type 2 item comes, I will withhold it. I will not submit, so that I have 1 type 2 item. If I already have 1 type 2 item, then for all the following type 2 arrivals, I'll just submit them, right? So I keep a safety stock level of 1. So why do I need a safety stock for? I need a safety stock to do internal matching with type 1 item. So when a type 1 item arrives, if I have a type 2 available, I do an internal match. I don't submit them. Okay, if a type 1 item arrives, I don't have a safety stock, then I will submit the type 1 item. Right, to summarize, I'm keeping a safety stock for the under-demanded item, and I use that to internally match my over-demanded item. This is my policy 2. With some calculation, we show that policy 2 strictly outperforms policy 1. Right, so an agent does have incentive to deviate. Right, by doing this simple twist, it can get better rewards. Right, it can game the system. And we try a lot of simple fixes. They do not work. Right, so for example, let's say we conduct a match in the Meta platform. Instead of giving all the reward to the submitter of 1, we only give 1 minus epsilon to submitter of 1 and epsilon to submitter of 2. For any choice of such epsilon, policy 2 still outperforms policy 1. Right? Still, you cannot remove the incentive to deviate. Any questions about this example? Great. So that just motivates us to think about the problem deeper. On one hand, we have this approximate Nash equilibrium for the marginal value mechanism is somewhat unsatisfying because agents may still easily find deviations to improve their outcomes. And this will reduce the predictive power of the mechanism, right? Because now the agents, they might not just follow the fully submission, right? They might deviate, they might withhold some. On the other hand, there's no hope in attacking the exact equilibrium. It's really challenging. Here we're considering a private information setting. So the equilibrium will be a perfect Bayesian equilibrium. Basically, all the agents, they will try to, based on their past interactions of the system, they will try to guess what's the state, what's the arrival at the meta platform, what other people are doing, keep updating their posterior, and make best decisions based on that. It's considered very impractical due to its very high knowledge requirements and high requirements of computation power. Right, so this has been mentioned many times in the previous literature that is impossible and unrealistic. Right, so what are the other solution concepts that we can use? Just to be clear, so here we are not trying to say, let's prove results for better solution concepts. It's the other way around. We want to find a solution concept that can motivate us to find better mechanisms. Right, more elaborate, more fine-grained mechanisms that can help remove the incentives for agents to deviate. And here comes the mean field equilibrium, right? So that's the solution concept we're going to use in motivating the next mechanism. So what's the mean field approximation here? What's mean field equilibrium? So mean field approximation actually is an approximation of the information structure of agents. Right? So in the perfect Bayesian equilibrium, agents try to guess what other people are doing, what their states are. But in mean field approximation, agents just assume the meta platform is in steady state. Okay, so what that means in our setting is, as an agent, when I submit a type J item, the probability it ends up getting matched is fixed. The probability is a WJ. And these WJ are determined endogenously. Right, so as agent, the only way I interact with the system is through the submission. Right, I'm just gonna assume the submitted items, the probability it gets matched is fixed. As a result, the agent's decision problem becomes a Markov decision process. Okay, so I'm just trying to mind my own business, solve this MDP. And what do I mean by equilibrium? These agents still have a conjectured matching probability in the meta platform. Let's call it W. And based on that, they solve their MDP, they have their best response. And the best response will induce a real matching probability. We call it H of W. If W coincides with H of W, it's an equilibrium. We call that a mean field equilibrium. So why is this more fine-grained than approximate Nash equilibrium in this setting? It's because each agent still need to solve an MDP. It's a dynamic problem. Although fluid approximation, they are not fine-grained enough. We need to carefully look at the MDP of each individual agent. So any questions about the mean field equilibrium? Great. Right, so here comes our mechanism. All right, so a key observation from all the discussions above is that even submissions of under-demanded items need to be rewarded, right? Although these under-demanded items have a marginal value of 0, you still need to somewhat reward them. Otherwise, the agents or hospitals, they will just withhold these under-demanded items, right? Withhold, make them safety stocks, and use them for internal matching. The problem is how to reward it. And here's how we do it, right? So to explain this mechanism better, I introduced the legend here. I will use this red color for over-demanded item, blue color for under-demanded item. Okay, so let's say now as an agent, you submit an over-demanded item to the meta platform. Okay, you submit this red circle. What do you get? You get PJ star minus epsilon. Remember, in marginal value, the NV mechanism, you get PJ star if it ends up matched. Here, I'm intentionally taking a cut. You only get PJ star minus epsilon. And this epsilon will be determined later, right? It's a small positive constant that doesn't depend on the system size n. Great. And what happens if you submit an under-demanded item, right? Let's say you submit this triangle. It's blue, so it's under-demanded. You get a credit, right? So don't think of the credit. The credit's like artificial currency, but there are many types of it. So for each type of item, there's a type of credit. So for example, you submit this triangle item, you get this hollow triangle, which represents a credit. If you submit this hexagon, you get this hollow hexagon, which represents a credit. Okay, and this credit, it also expires. They don't live forever, but they expire at a slower rate than the physical item. Right, let's say this blue triangle, the average lifetime is 3 months. But this credit, this hollow triangle, its average lifetime is 6 months. So you are swapping your short-living physical item for longer-living credits. And how do we use these credits? That's the last piece of the mechanism. Okay, so instead of doing these isolated submissions, you can do the following. You have a physical over-demanded item. You can pair it with under-demanded credits, right? So compare this red solid circle with these 2 credits, okay? If they can form a match, right? It's called a virtual match. You just submit this item together with the credits to the system. Submit a whole match to the system. And what do you get? You get the whole shadow price of the over-demanded item. Okay, let's say this over-demanded item shadow price PJ star, you get the whole PJ star instead of PJ star minus epsilon. So these credits, they do help you, right? They help you gain more. Now the platform won't take a cut of minus epsilon, it will give you the whole thing. And this match is virtual, right? You don't need to perform the match. It's just if this match is possible, then you can submit everything together to the platform. Any questions about the mechanism? Great. So let's take a closer look at this mechanism, what it does. Right? What it's trying to do is to give agents a motivation to submit under-demanded items. Right? So by submitting under-demanded items, they get longer living credits. And this credit can be useful in helping you get more reward by doing these virtual matches. And here's our performance guarantee. All right? So in a word, we show that under the MVC mechanism, full submission is a mean field equilibrium, aka oblivious equilibrium, for large enough but finite size system. Okay, the only requirement we need is the meta platform should be doing something asymptotically optimal. And also the credits, they should depart at a slower rate compared to the corresponding physical items. And if everything holds, if all of this holds, then we can find this design parameter epsilon for it to work. All right, so if you are using a smarter matching policy at the meta platform, how does that affect this result? It will make the threshold n lower, right? So I mean, for a smaller system, we can still get this result. Any questions? Great. I think we are on the right pace. So just a little bit about the intuition of theorem 2, right? So why does this MVC mechanism work? The proof actually is pretty long, but here, let me try my best to summarize the intuition, right? Because now we need to analyze the MDP. So a fluid level analysis is not enough, right? So we need to actually look at the timing of a match. Let's look at the following match, which has 3 constituents, 1 circle, 1 triangle, and 1 hexagon, right? So let's say that the circle arrives first, then the triangle, then when the hexagon arrives, we do the match. Right, so in this match, we call the first 2 items active items because they actively wait, right? And there is a passive item. This passive item, it doesn't wait. For each match, 2-way or multi-way, there's 1 passive item, and all the earlier ones are active items. Okay? And in this match, there's 1 over-demanded item and 2 under-demanded items. So what we are trying to do is the following. So we need to do a careful analysis of agent's best response, which is the optimal solution to an MDP. But this MDP, we cannot solve it exactly. We don't have the value function, right? So we need to use the coupling argument. Right? We need to couple with the optimal solution, comparing submission versus no submission, and try to rule out those suboptimal decisions. And in the end, we show that yes, it is optimal for the agent to submit everything. And that's the best solution for the MDP. So we proceed in 2 steps. We first show that you never let an over-demanded item wait. Over-demanded item is never active. The intuition is straightforward because waiting is risky. If you let it wait, there's some probability it will depart before finding a match. You might as well just submit it and lose its only epsilon. You get PJ star minus epsilon. Okay? And then a more difficult part is to show even for under-demanded item, you don't let them wait. So why is that? There's benefit of waiting and there's a cost of waiting. So if you submit, if you don't wait, what do you lose? If you submit them, if you submit them, what do you gain? What you gain is you swap them for longer living credits, right? So these credits will be useful in the future. In some unfortunate event, that if you don't submit, the things will all leave the system. But the credits, because they live longer, they don't leave the system. So it helps you make more matches in the future. Okay, so using some regenerative renewal theorem arguments, we can show indeed the benefits of submitting outweighs the cost of submitting. So even for under-demanded item, you don't let them wait. But if you don't let over-demanded item wait and you don't let under-demanded item wait, it means you submit everything, right? That shows full submission is the optimal response. Okay, any questions about this proof? It's just a very rough sketch, but that's the rough thinking behind the proof.
Could I?
Hi, Shane. Hi. Yeah.
So you mentioned this coupling argument. In that coupling argument, are you trying to sort of balance the that immediate reward you'd get versus the reward you obtain from the credits, and somehow the credit, because these have got longer life, they earn more reward across the cycle?
That's correct. Yes. Right. So basically, we construct these events. Under these events, the physical items will depart, but the credits, they don't because they live longer, right? So when this event happens, if you submit, you get one more match, right? And using this regenerative argument, we show, okay, so that gives you enough benefit of submitting.
Nice.
Yeah.
Nice. Okay, thank you. Yep.
Great. Thank you. Yeah. Great. And that's pretty much everything I want to cover right on time. So in this talk, we talk about the motivation for a decentralized dynamic matching setting. That is, we try to get rid of free riding. We try to make sure everyone has incentive for full participation. And we propose two mechanisms. One is the marginal value mechanism, under which we show full collaborations approximate Nash. The other is the marginal value plus credit mechanism, under which full collaboration is a mean field equilibrium. And I want to point out the version of this paper online is a little bit outdated. It only contains half the results. We'll be uploading the full version very soon, maybe in 1 week or 2. Thank you very much.
So we are right on time. So maybe we'll just seek 1 or 2 questions from the audience, if there are any.
So maybe I could ask another while we wait. Oh,
yeah, let's go ahead.
Yeah. So very quickly, Sushil, sorry. So the marginal value plus credit, that's not asymptotically optimal. I guess it's actually optimal at sort of any scale. Is that true?
If for large enough system size, large enough N.
Ah, okay. So
right.
Good, helpful. So is it the case then that the N and that you need to achieve and the sort of the intervals you have to wait for, are they realistic for kidney exchange?
Right. So actually, we did some preliminary simulations using the size of the arrival rate, number of hospitals. It turns out if you only have 50 or 100 agents, you already get very good approximation, right? Mm-hmm. This dependence on N is mainly through when you submit an over-demanded item to the Meta platform, you want it to have a high probability of being matched because in Fluid, it's 100% matched, right? As long as it's pretty close to 1, you get this result. That the full submission is optimal thing to do.
Well,
right? So that's where N comes in. Yeah.
And is the 50 to 100 hospitals, is that sort of realistic for what's being considered right now?
So in the US, I think the number is 100 something. Yeah, 100, 200, the number of hospitals that have their exchange pools. Yeah, and from this this survey paper, they do have some arrival rate numbers of all different kinds of kidneys. Yeah.
Great. Okay. Thank you.
Yeah. Thank you.
Hi, Pengyu. Very nice talk.
Thank you.
I really liked the theorem too. And so I was wondering, it seems like your Meta platform, the centralized platform, is not really making any money by allowing for these matches to be made.
Right. That's
because
correct.
like whatever value you are generating, you are just giving it out to the other smaller platforms.
Right.
So I was wondering, in some cases, seems like it is possible to make some money for the Meta platform. For example, if one platform, if you have only 2 items, and one platform, the arrivals are only for item 1, and for the other platform, the arrivals are only for item 2, and the Meta platform is trying to match these 2 items together, then the Meta platform can earn revenue while, and the 2 platforms must submit. So this is like a trivial example.
I think you are right, right? So you are basically saying, okay, so if I pull things together, can I get more reward that's enough to incentivize everyone? I still have something left, right?
Correct, exactly.
I think it's possible. Yeah.
Right.
Yes.
So does that kind of not show up in your setting, and why does it not show up? Because like in your case, you're not really thinking about that.
Right here, I'm just satisfied with, okay, so that provides enough incentive for everyone. That's good. If I have
see.
some leftover, I can just randomly allocate them to the agents so they have more incentive. I did not consider like what's best for the Meta platform, because here Meta platform is like a construct in the mechanism, right? It might not be an actual platform. It could be just smart contracts or an algorithm running in the background.
Okay.
Yeah.
So then I guess a question in that lines one could ask is, can you then maximize the profit for the Meta platform while making sure that you have a Nash equilibrium for the all the other platforms?
Yeah, I think that's a legit question. Yeah.
Okay. Cool.
Great. Thank you, Sushil. Yeah.
Thanks.
Hi, Pengyu.
Hi, Wental.
I have a question on the modeling.
Yeah.
Because when I think of the reality, when you pull the kidney pair across different hospitals, the difficulty seems to increase by matching patients from different hospitals, right? Because they may be of different distances. And I wonder whether your model can incorporate this kind of decreased reward when you try to pool resources.
I see. That's a great question. So basically, you are saying there's some like frictions and cost.
Yes.
Like this hospital in California, the other in New York, doing the match is more costly than matching between 2 New York hospitals. Yeah. So I'm not, to be honest, I'm not entirely sure if we can still have this nice result. I think our result does have some robustness, right? Allow for some small perturbation, but I'm not 100% sure. Right, in the earlier paper that incentivized collaboration between queuing, in that one we show it's possible, right? If serving other people's job is more costly than serving yours, we still have this resource pooling result. But here I'm not entirely sure.
Got it. Thank you.
Yeah, thank you.
Pengyu, I have a last question. So regarding the 2 mechanisms.
Right.
So the marginal value mechanism would already work well without incentives to deviate if the number of agents is large. And then, so the second one, so the refined mechanism with credit also works well for sufficiently large N. So my question is, let's say in your numerical example with the hospital, do you actually, so with that given with a particular N, do you observe that the second mechanism works better for this finite system?
Right, that's a good question. So I think first, theoretically, the difference between these 2 results is for the NV mechanism, you get approximate Nash, right? So no matter how large the system is, you still have some room, some incentive to deviate, although it's increasingly small. But for the latter one, it's like once the system is large enough, there's no incentive to deviate. You can perfectly safe in saying people will follow the fully submission response. We're still trying to finish up the simulations. We have the gap for the MV mechanism, but the MVC is likely harder to simulate. But we are trying to do it. Yeah.
Okay, great.
Great, thank you, Yue.
Yeah, thank you. So I think that will conclude today's seminar. Thank you, Pengyu, for this very interesting work and the great presentation. Okay, so we'll see everyone in our next SNAPP seminar.
Great, thank you. See you next time.